Welcome to Encoding Diagnostic Codes using privacy-preserving record linkage techniques. My name is Christian Borgs and I am a researcher at the University of Duisburg-Essen. Today we're going to talk about encoding diagnostic codes in privacy-preserving record linkage. One of the most used codes in diagnostic settings are, of course, ICD-10 codes, which are used to classify illnesses. Examples include biology, the classifications of occupations, accident statistics, not employment codes, and ICD codes. These are often sensible information in a way that you would not want to disclose the ICD code of a patient to anyone else. Therefore, they usually have to be encrypted in some way, and this is going to be a lecture about how to do this using a privacy-preserving record linkage technique called Bloomfilters. We here present the hierarchy-preserving Bloomfilters that are used to encode hierarchies in Bloomfilters. To do this, we first have to think about some priors. Assessing the similarity of hierarchical codes usually involves knowing the code positions and their relative importance. For example, in ICD codes, the first letter is the chapter of diagnostic codes, including several things like diseases of the heart, diseases of the lungs, or cancer type illnesses. These, of course, should correspond closely to the ones that you encrypt, meaning the first positions are more important than the last positions. So if they are close, an exact match is of course a good idea, but it's not required. If only the last code position differs, it should be more similar than, say, a naive approach would suggest. We are also testing these methods against a standard privacy-preserving record linkage setting where we are using these diagnostic codes as an additional identifier. This is something that we think would enhance privacy-preserving record linkage. To compare the method to the naive approaches, this is the standard Bloomfilter construction for two first names. Now you can see that these are split into bigrams and hashed 2 times each. You could also think about doing that with a diagnostic code, where you would have a simple unigram for each code position that would then hash several positions. You can also think about the fact that this is not hierarchy preserving because it will give the same weight to each of the positions, meaning in this case it does not matter whether the SA bigram is first or last, as is obvious with the RA bigram, which it doesn't matter which position in the name it is in as long as it's in the name. You can see you can approximate clear text dice coefficients relatively easy with this method, and therefore has been used in privacy-preserving record linkage for about 10 years now. Hierarchical information, of course, is different in the way that chapters, groups, and subgroups of diagnostic codes do matter a lot. Here are some examples. For example, the diseases of the respiratory system are the chapter J, while the circulatory system, like heart failures, are in the chapter I. So the first position matters a lot. The second, the groups are 2 parts. They matter a lot, of course, but the subgroups themselves, the last bit positions, they are not that different anymore. They are very close to each other, so they don't matter that much. Of course, using these 4 digits as an input for a Bloomfilter would make them lose every information that they have. To remedy that, the code positions could be added to the simple parts of it, meaning you could add a number to the chapters, like 1. You could use a number that will designate the groups and the subgroups, and you will add that as a part of the unigrams, meaning you will get positional unigrams, which have been used before, meaning the first position gets a 1, the second position gets a 2, the third position gets a 3, and so on. This would now map more elements into the Bloomfilter that are distinct, even though they are possible duplicates, meaning that if you have an ICD code that has a lot of zeros in them, like J100, the influenza, this would usually lead to the 0 being omitted, at least the last 0 is being omitted because the 0 is already hashed into the Bloom filter. This way you would get 2 zeros because they are 2 different bit positions. So we expect this to perform better relative to a naive approach because we are going to preserve some information that is positional. But we are going to propose the hierarchy preserving Bloom filters for this. We will use each position to hash different amount of positions to 1, meaning the first code position, the I, will get more hash functions relative to the later positions. You can see this in the amount of hash functions at the lower part of the image before they are hashed into Bloom filters. You see that the first code position has much more code positions that it is hashing compared to the last code position, which is designated as S1, which only hashes 2. This is possible by not just hashing the code positions themselves, but we're going to use a modifier that is going to multiply the code position with a static number, and that is called C here. You can see it's a stream length modifier of 2, meaning each of the bit positions gets twice more bit positions that are set to 1 than the one before, meaning you will get 8 times as much bit positions in the first code position than the last code position, and this should give more relative importance to the later to the first bit positions, code positions. To evaluate this, there are several things that are of importance. Of course, a full match of codes in clear text and in encrypted form should give a higher similarity than only partial matches. And of course, you want these categories where subgroups differ or just the last position differs should be more similar than, say, a nearly total match. This is possible with ICD-11 codes, this time with the 6-digit classification of Klug et al., which is basically from no code positions differ, which is a full match, to all code positions differ, which is a full non-match. And between these, you should be able to discriminate the categories, because each code position that differs is then a lower similarity. And ideally, you would see that these don't overlap as much. And we're going to use that to evaluate the similarity preserving properties. So for the standard Bloom filters, these are the box plots for each category, where the left part is the full match and the right hand side is the full non-match. And you can see the dice similarity that can be between 1 and 0, a full non-match. However, you can see that they are all over the place. There is a trend, of course, but there's a lot of variance between the categories when using a standard Bloom filter to encrypt these diagnostic codes. If you use positional bigrams, you can see it like this. It gets slightly better, but it's not very good. And in contrast, these are the hierarchical Bloom filters, where you can see that they are very much able to make a distinction between these linkage categories. You can see this quite obviously, that this is quite the improvement. So this, for example, shows that full non-matches are much, much closer to a 0 dice similarity at the median than, say, the next category, where only the diagnostic chapter is wrong. To add to that, linkage quality for a privacy-preserving record linkage setting is something that we briefly touch upon using a cryptographic long-term key, which is a composite Bloom filter of first name, last name, date of birth. So these are always there in all of these settings, and you can then add the diagnostic code to this as an additional identifier. The standard Bloom filter approach is the red one, the yellow one is the positional Bloom filter, and the blue one gives you the hierarchy preserving Bloom filter with a stream length modifier of 1. And you can see that the privacy preserving record linkage performance over all thresholds except for, of course, the exact match threshold, which is a 1, improves quite a bit. So, and for many research applications, codes representing hierarchies are used, and if they have to be encrypted, most encryptions will totally lose all information that is in the hierarchies themselves or in the codes themselves. So we tried to show a method for hierarchy preserving Bloomfilters and demonstrated that it is more feasible and better at preserving hierarchies than using standard approaches. It also yields better PPR linkage quality results, which is a plus. So if there is ever a situation in which stable ICD codes from 2 data settings can be used, hierarchy preserving Bloomfilters as an addition to the standard Bloomfilter methods are a good idea. So this concludes our presentation. Thank you for your time.